Alright, this is Mr. Halsey with H Squared Sufficiently Understood Science, and today we're going to be looking at the reasons for the seasons. So in our last lesson, we discussed how the rotation of the Earth creates the night and day cycle, and that the revolution of our planet takes 365 days. So just a quick refresher right here. Earth, okay, that is, I'm going to put a little arrow going like this because it's spinning on its axis. That is our rotation. Okay, and over here, oops, wrong color, wrong button. We have the sun right there. Once again, this is going in a counterclockwise motion. And so here we have our revolution. Unfortunately, though, we can't really feel the Earth orbiting, so we primarily notice the passing of the year through seasonal changes. Now, the big question is, what causes these seasons to occur? You may have heard it explained like this, that these seasons are caused by the changing in distance between the Earth and the Sun. And it's warmer in the summer because Earth is closer to the Sun during summertime. You may have heard it explained like that before to you, but unfortunately, that is 100% wrong. It's a common misconception that the Earth's summers are caused by our proximity to the Sun. In fact, in the Northern Hemisphere, during our winter months, we're actually closer to the Sun than we are during our summer months. And that's in the Northern Hemisphere. So the problem with this idea is that when it's summer in the Northern Hemisphere, it's winter in the Southern Hemisphere. They're exact opposites. So if it were true that the seasons were caused by the proximity or closeness to the Sun during different parts of our revolution and orbit, then both hemispheres would be experiencing the same seasons at the same time. Furthermore, the distance between the Earth and the Sun only really varies about 3% during its orbit. Now, yeah, the Sun is 93 million miles away, and 3% of 93 million miles away is still thousands of miles. But kind of consider it like this. If you were asked to walk across a football field, okay, or even let's make it smaller. You were asked to walk across a room in your home. For you, that's not a big deal. You can walk very easily. It's not a long, arduous journey. But if you were shrunk down to the size of an ant, then it would be a long journey. It's in perspective. As far as distances in the solar system go, 3%, a few thousand miles, that really isn't all that much. Nothing that is significant enough for our planet to have seasonal changes based on its proximity to the Sun. But in fairness, there are planets that experience seasonal changes not only because of an axis, but also because of proximity to the Sun. One notable one, or at least it used to be a planet, is Pluto. It has a very eccentric elliptical orbit. So its seasons change drastically because of its proximity, how close it gets to the sun. So June 20th is the beginning of summer. The beginning of summer. And we call this the summer. Oops. If I can get that to work. Summer solstice. Now I'll point out a little bit right here. Sol is the name for our sun. Okay? And so the summer solstice is when the sun is highest in the sky. It's the day that the sun is highest in the sky. Because the Earth's axis, and keep in mind, this is all relative to the northern hemisphere. It's going to be the exact opposite in the southern hemisphere. So during the summer solstice, the Earth's axis is facing towards the sun. So if I were drawing a little terrible sun right here, and an equally as terrible Earth, oh, that is bad. Okay, even I can't accept that. There we go. That's a little bit better. Okay. The axis of the Earth for the northern hemisphere, I'm going to draw the equator. The axis of the Earth would be facing toward the sun, while the southern hemisphere's axis is facing away. So this axis faces towards the sun. So in summer, the sun takes a higher arc in the sky. And we'll talk about it again here in a little bit, but I want to go ahead and explain it. During the winter solstice, which is going to be shorter days, the sun will take a much more low angle through the sky. Its arc is much lower because essentially we're looking at the sun at an angle. It's not, the direct sunlight's not right on us. Now, because summer is the time that we get our most direct sunlight, the days are going to be longer and hotter due to that direct sun rays hitting the Earth. So September 22nd is the beginning of fall or autumn, and this is what we call the fall equinox. So this word equinox is going to tell us a lot about what's happening with relations between the sun and the Earth. So you can kind of think about it like this: equinox meaning equal. So both hemispheres will receive the same amount of sunlight because neither end of the Earth's axis is tilted towards the sun. And I'll explain more about why that is in just a little bit. So equal sunlight. And that's because the equinox, and during the equinox, the sunlight is shining directly on the equator. And so that tells you a lot about, what's going on. And so, fall is the time where the leaves start coming off the trees because we're going from a time of a lot of sunlight down to less sunlight because of the tilt of the Earth. And so we start to see, this is the fall and autumn are the intermediate changes right there. I'm going to redraw that. Okay, it's the what's happening in between summer and winter. So as we're going here, we're losing sunlight, and so organisms like plants are going to react, because especially plants, because they rely on good old photosynthesis. And photosynthesis uses light. And so they're going to go into hibernation because of this, because of the lack of sunlight. They'll drop their leaves in order to conserve energy. December 21st is the beginning of winter. The days are shorter and the nights are longer, and so December 21st is our winter solstice. And we'll talk more about solstice and things like that in just a minute. But this is where, like in that other diagram I showed you, where the sun is at its lowest point in the sky. Remember, Sol, sun, okay, its lowest arc in the sky as compared to summer, which would be up here. And so the days are shorter and the nights are longer. And this is because the Earth's axis is tilted away from the sun. So if I were to draw this out a little bit, here's our terrible sun once again. Nice to meet you, nice to see you. And my equally as terrible Earth. Okay, so here the equator is now right here because of our revolution. Okay, and the axis, and of course, you know, we're looking at it from a different perspective. So I want to make that clear. Okay, so when we did the original example, you have to remember we're moving in a circle. I put the sun in the same place. And so we're looking at it from a different perspective. We've moved here. We'll come back over here and we'll still have that same angle later on. So just keep that in mind. We're looking at it from a different perspective. So the axis doesn't move. And I realize that that can be a little bit confusing. So in this example, the southern hemisphere is pointing towards the sun. So it's summer, and the northern hemisphere is pointing away from the sun. So it's winter. And less direct light is hitting the northern hemisphere. Then we round everything out with March 20th, the beginning of spring. So this is our spring equinox. So remember, EQU, equator. That's where the light's going to be shining because neither end of the Earth's axis is tilted. And another thing is equal, because both the northern and southern hemisphere are getting the same amount of sunlight. Strangely enough, so just like in the other example, there's really actually not much difference between spring and fall. Both have very similar temperature ranges, about 70 to 80 degrees. They have the same amount of light in them, at least at the equinox. Our biggest thing is that we see a shift in plant life. And so we're going from winter, right, that had very little sunlight working with it, to summer, which has lots of sunlight. And I know that's way bigger than the other example, but you get what I'm trying to say. So here we have winter, here we have summer, and spring is the area in between, the transition period. So just keeping this in mind, whatever it is in the northern hemisphere, this is the northern hemisphere right there. So if it's winter in the northern hemisphere, that means it's summer in the southern hemisphere. So if you're planning a trip over the winter break and you're going from Texas to, let's go to Australia. Okay, so you're going to Texas to Australia. Well, here it's winter. You might be wearing a coat, but when you get to Australia, which you're going to take this path, okay, so when you get to Australia, it's going to be summer. It's going to be completely different temperatures. It's going to be warm. It's going to be right around the peak of their summer solstice. If you leave during the middle of, during December. So it's going to be very warm. So you don't want to pack coats or anything like that. So just keeping in mind, the equinox is one of two opposite points. Here is, I'm going to label these as E. Okay, I'm going to make that a little better for you. So that's an equinox, that's an equinox. On the celestial sphere where the celestial equator and ecliptic intersect. So in other words, where the axis is neither pointing towards or away from the sun. Okay? It's neither pointing towards or away. Now the solstice is either of two times of the year where the sun is at its greatest distance from the equator. And I'll show you guys what that means in just a second. And so okay. And that shouldn't say fall solstice, that should say summer. Oops. So where does the sun shine during an equinox and during solstices? So welcome back, our terribly drawn sun. I'll do a little bit better this time. Okay, so there's our terribly drawn sun. And there's our Earth. So our equator, I'm going to put it at an angle here because we are tilted. And this is going to be our axis. Okay. And so during the equinox, first, let's start with the fall and spring equinox. The rays of the sun are going to be pointing most directly right at the equator. Okay, so that is 0 degrees north-south. The equator is 0 degrees. So during the equinox, it's pointing right at the equator. Now we're going to do this relative to the northern hemisphere really quick. So during the summer solstice for the northern hemisphere, the sun is going to be pointing more directly at the tropic of Cancer. Okay, and that's because right now the Earth is pointing towards the sun with its axis. So it would be summer in the northern hemisphere here. Now, during our winter solstice, the sun is going to be pointing more directly at the, and I know that's not a straight line, at the Tropic of Capricorn. So what's really interesting about these two lines, the Tropic of Cancer and the Tropic of Capricorn, so during the winter solstice, you see the sun's shining directly on the southern hemisphere, okay, during our winter solstice, and so that's why the sun, doesn't have as big of an arc in our sky. But this also helps us to figure out the tilt of the Earth, because the Tropic of Cancer is 23.5 degrees north, the highest point that the sun rises on our planet. The Tropic of Capricorn, 23.5 degrees south, the lowest point that our sun falls during the winter solstice, throughout the sky. And so this really helps us see how this works. So during the summer solstice, it'll shine directly on the Tropic of Cancer, so that's our summer solstice. During the fall and spring equinox, it'll fall directly on the equator at 0 degrees. And during the winter solstice, it would fall in the Tropic of Capricorn, 23.5 degrees south beneath the equator. Now, areas in between here, between the Tropic of Cancer and Tropic of Capricorn, tend to get the most direct sunlight throughout the year, and so they are going to have very little changes in their seasons throughout the year. So Earth's rotational axis is tilted by 23.5 degrees with respect to a line drawn perpendicular to the plane of the ecliptic. So that's what I'm going to do. I'm going to draw a line right here. So that's the plane of the ecliptic right here. And so that's the orbital plane of the Earth. So there's Earth's rotational axis, and there's that 23.5 degree tilt. So the seasons result from this tilt of the Earth's axis and rotation. And that's true not only of the Earth, but also any planet with a tilted rotational axis. So the direction of the rotational axis is going to stay nearly fixed in space. We're going to talk about something a little bit later that's going to change this a little bit, but don't worry about it just yet. While the Earth's orbit, so it's going to remain fixed in space while the Earth orbits the sun, and the hemisphere that seems to lean into the sun or points towards experiences summer, while the hemisphere that leans away or points away from the sun experiences winter. So right here we have a little diagram. And what you'll notice is that the axis, and that's the first thing you should always look at when you do any of these, the axis right here, the northern hemisphere is leaning away, it's pointing away, and the southern hemisphere is pointing towards it. And so it'll be winter in the northern hemisphere and summer in the southern hemisphere. Now, as it goes around, that axis is going to remain pointed in the same direction as it goes around the sun. And so right here, this to go. If you look at this, neither one of those arrows are pointing towards or away from the sun. And so this would be an equinox. This is a solstice. Over here, one pointing towards, one pointing away. We can definitely see one's going towards it. And so this is a solstice. Sorry about those stray marks. Right here, we have one pointing away and one towards. Or sorry, neither one are pointing away. And so this is an equinox. And so if we go through this, we'll see that the Earth will go through these positions. And 6 months later, it's now summer in the northern hemisphere and winter in the southern hemisphere because it's pointing in different directions. So the tilt of the Earth's rotational axis naturally explains why the seasons are opposite in the northern and southern hemispheres. And so if this was the winter solstice for the northern hemisphere, then this would be spring in the northern hemisphere, fall in the summer, or in the southern. Here we have summer in the northern hemisphere, winter in the southern, spring in the southern, and fall in the northern. Now it's important to look at the axis for any question like this, because in reality, we could place the axis in different directions because we may be viewing it from a different angle of the solar system. So you have to keep that in mind. So as the sun as the Earth goes around, we see different levels of daylight that are going to be placed on the Earth. So during the summer solstice, in June, the North Pole will have 24 hours of daylight. During the fall equinox fall equinox at the North Pole, it's going to have equal amounts of sunlight. So it'll actually have basically like it's sun setting pretty much. The South Pole will have the sun rising. During the winter solstice, the North Pole will have no daylight whatsoever, and the South Pole will have 24 hours of daylight, and it's all because of the tilted axis. So let's take a look at an example question. So right here, the diagram shows 4 positions in Earth's orbit around the sun. The northern hemisphere experiences the beginning of spring when Earth is in position 1, 2, 3, or 4. And so let's go ahead and underline our most important things. Definitely want to underline northern hemisphere because that's what we're looking at. And we're looking for when the beginning of spring is. So I'm going to make sure I know where my axis is. There's one of them. There's another, and another. So I know what direction my axis is towards the sun. So I'm going to label that like this. Come on. I think I need to clean my screen. You notice it doesn't change what directions I put the arrows. It doesn't change, but the Earth's location does. And so right here, let's start with 4. Okay, so the northern hemisphere is leaning towards the sun, so that means it's summer. This would be winter. Right here, neither one, so it's going to be an equinox. So we can assume, though, because logic, what comes after summer, this would be fall in the northern hemisphere. This would be spring in the southern. So right here, the northern hemisphere is facing away, more away. So we have winter, we have summer, and right here, neither one. So what comes after winter? Spring. And this would be fall. So position 1, it is fall in the northern hemisphere. Position 2 is winter. Position 3 is spring. And position 4 is summer. And we are looking for spring. So it's not position 1, it's not position 2, it's not position 4, and so our answer must be C. So the hemisphere experiencing summer, for the hemisphere experiencing summer, sunlight striking the earth is more concentrated, and this helps to raise the average temperature. And the reverse is true for the hemisphere experiencing winter. The sun's going to be higher in the sky for longer during summer days and lower in the sky for a shorter number of hours on winter days. During spring and autumn, the two hemispheres receive approximately equal amounts of sunlight. So when the sun is higher in the summer sky, the sunlight is more concentrated. It spreads out over a shorter distance. But during the winter, the sun is lower in the sky and comes at the earth more at an angle. And so it's diffuse sunlight, or spread out. The same amount of sunlight covers a larger area. And so that thermal energy gets spread around a lot more, resulting in it being cooler. So the equator, which is right here in the center, is where the subsolar point is, where the sun will shine directly on the earth during the equinoxes. And I love this diagram because you can really see that as you go up, the sunlight becomes more and more diffuse. And the reason for that is the curvature of the earth. Even if we didn't have a tilt, these areas would be colder because they are curved. And so it would be cooler at the top than it would at the bottom, or in the middle, excuse me. And so this is a really good diagram. So this is the same amount of sunlight. If you look, the amount of sunlight for each of one of these is the same. But these lines keep getting longer and longer because the sunlight is having to spread out over a much larger distance. Okay, so what we're going to do is we're going to take a look at how the Earth is going to be moving. So right here we have the profile of the Earth, and this is showing the vertical rays of the sun. So we're going to start here in March at the March equinox. Now, remember, this is going to be spring in the northern hemisphere, fall in the southern hemisphere, but there's not really much of a difference either way. And so I'm going to go ahead and start moving this guy around. So as we go, we're going to get over here. I'm going to try to get it. There we go. Oops, let me go back a little bit.
right there. So here we have the June solstice. So we have 24 hours of daylight at the Arctic Circle and 24 hours of darkness at the Antarctic Circle down here. So this is where the vertical rays are going to be striking the Tropic of Cancer most directly. And so the equator is still going to have about 12 hours a day. And so this is going to be summer in the northern hemisphere and winter in the southern hemisphere. Because you see how the light isn't hitting the southern hemisphere as directly. And as we keep going, we're going to come over here into the northern hemisphere's fall. One thing I want you to keep in note really quick is that the northern southern hemisphere, neither one of these are facing directly away, so they're equal. So all locations of the Earth are going to experience 12 hours of daylight here. So everything's equal. The equator is getting the most amount of sunlight here, most direct sunlight, during the equinox. As it keeps going, it keeps going, it keeps going, we see a shift where we now have 24 hours of darkness at the Arctic Circle and 24 hours of daylight at the Antarctic and Antarctica. And we can see the vertical rays of the sun are striking Capricorn most directly. And we'll just go back to where we started here. Anyway. There we go. With the even sunlight. So let's take a look at how the angle, our inclination angle, makes a big difference. If you look here, our axis angle is at 0. And so the sun's always going to be coming right across the sky. What I'm going to do is I'm going to trace the sun's path here. And I'm going to speed it up just a little bit. And so what you'll see is the sun rises and falls in the same position every day. And the temperature doesn't change either. And that's because there's no change whatsoever in our tilt. It's at 0 degrees. So we're going to stop that. We're going to clear our trace here. And what we're going to do is we're going to set this to R's. So our location is right there at that X. And so we're going to have this thing start going. And what we'll notice as we go around, okay, is that the temperature will change. So right now the northern hemisphere, our little X, is actually pointed away. We're getting less direct sunlight, and so the temperature is relatively cool or cold. Now we're gonna get this going a little bit faster, and you'll see right here how the sun is starting to rise higher and higher because the northern hemisphere is facing towards it. Starting to face towards it. We're gonna keep going right here. About right here. You notice the temperature is getting warmer and warmer as we go. We're now in summer. Here's our summer solstice. And the sun is rising higher and higher in the sky. As we move towards winter, lower and lower because we're getting less direct sunlight. And you can see that right there by the sunlight angle. Now planets like Venus, which have a 2-degree tilt, has basically the same temperature all year round. So it's not having a lot of change. But other planets like Uranus, which is actually on its side about almost 90 degrees at 86, let's take a look at what that looks like. So the sun is basically right here. We're at this X. The sun's cooking this side of the planet like for half the year. And then it gets dark. You get a couple of daylights, and then it is dark again. Now, kind of showing you a difference in the length of the planet's Earth and day nights. So as our planet moves, because of the axis, as we move into winter, that Arctic Circle right here is going to have 24 hours of sunlight. And so as we move from summer to where we have 24 hours of daylight because of the angle of the sun, or angle of the Earth's axis, we'll actually see right there. And so the Earth just isn't getting the amount of sunlight right there that it would need. So if we were looking at January, which actually, let's go to December. So this is where we're roughly at about right now. And so this is going to be 24 hours in night, 24 hours a day, 7 days a week, nighttime. Okay. Now, as we go into January, February, you see it start to recede because we're going closer to the equinox. March, April. So we've passed, actually, let's go back right here. So right there, March 21st, we have our little equinox going on. So it's equal. It's equal. So we get into April, May, June, July. You see it starting to go, creep its way back as we move towards fall and then to winter.
So let's take a look at another question. A student draws the models shown below. Which of these best compares the conditions at location X and location Y? So, is day at location X and night at location Y? Is winter at location X and summer at location Y? There are more hours of daylight at location X than at location Y. The moon is brighter when viewed from location X than when viewed from location Y. So let's take a look at this. So we want to compare conditions. We want to compare the conditions at location X and location Y. All right, so let's start with what we can determine from location Y. So here's our axis. It's pointing away. This one's pointing towards. Location Y is in the northern hemisphere. Location X is in the southern hemisphere. So let's see what else we can figure out. So it's not at the equator. They're pretty far off. So location Y, because it's facing away, would be in winter. So winter means short days, long nights, cold-ish, depending on where you are. Southern hemisphere is in summer. So that's long days, short nights, hot. Also, we could probably add in, based on what we just saw, less sunlight because it's diffused. More sunlight. Well, more concentrated. There we go. And so let's see what our choices are. So it is day at location X and night at location Y. Well, actually, if you look at it, they're both on the same side of the planet here. And so this would be the night side right here. Let me actually do this. So they're both located on the day side. So A is not an option. It's winter at location X and summer at location Y. Well, we know that's not true because we looked at how the axis is tilted. And so that is incorrect. There are more hours of daylight at location X than at location Y. Now that one is true. Now remember, we're looking for what best compares it, so we need to double check our last answer. The moon is brighter when viewed from location X than when viewed from location Y. No, that is not true. We have nothing in this model showing anything about a moon. Therefore, we're not even going to do that. And the moon doesn't work that way. So our answer is C. Now, during its yearly orbit around the sun, the Earth's rotation axis is fixed in space. It's always pointing in the same direction. That's why we can always look at the North Star for direction. However, we could watch the orientation of the Earth's rotational axis over a very long time period of about, let's say, 26,000 years. We could see that, in fact, it precesses, or actually it moves in a circle. So the precession of Earth's axis is due to a gravitational tug of war on the Earth by the sun and the moon. The sun is pulling at the axis a little bit like this, and remember folks, this is not to scale. The Earth is nowhere near this big compared to the sun. The moon is nowhere near this big compared to the Earth or the sun. This is definitely not to scale. More like if this were to scale. There you go. We are a tiny little blip. But anyway, the sun's pulling on the Earth at kind of an angle. The moon is offset. It's not at, perfectly around us. And so it's pulling at a little bit of an angle as well. And so what this ends up doing is it causes the axis to move slowly over time at 23.5 degrees around in this big circle. So the Earth's rotation creates an equatorial bulge, meaning the Earth is actually fatter at the equator than at the poles. So Earth's tilt means that the sun and moon are not aligned with the equator because it's being pulled all the time. And both the sun and the moon try to pull the Earth's equatorial bulge closer to it because they are exerting gravity on us. This is what's going to create our tides in a later lesson. So the combined pull of the sun and moon along with the Earth's own rotation results in that observed precession. So essentially, this is us right now. Okay? Winter occurs right here for the northern hemisphere when we're closest, and summer occurs right there. But because of the interaction between the pull of the sun and the moon, our axis will precess. It'll still be 23.5 degrees, but it will precess, moving in a counterclockwise motion. So in 5,250 years, our summer will be where our equinox is, where our fall equinox is, and our winter will be where our spring equinox is. And so we would have spring here and fall here in our orbit. In 10,500 years, we'll be completely flip-flopped. Summer will be over here at our closest, and winter will be over there. And so over the course of a little over 23,000 years, we'll make a full 360 degrees and be back where we started. So as far as effects for precession, the world atlas, the map of the Earth, will not change. The stars in the sky won't really change because we're still going around the sun. The only difference would be the location of our North Star. Polaris will no longer be our North Star, and so the celestial north will be different. We'll still have all 4 seasons. The tilt of the rotational axis is not going to change, but the timing of the seasons would be changed. Summer would be in January and winter would be in July. Now, the patterns of the stars in the sky wouldn't change much, but their positions to the celestial north would be different because we've changed our celestial north. And that's the reason for the seasons. I hope you enjoyed this tutorial. Please like, comment, and subscribe. And click the bell notification to know when we post a new tutorial. See you next time. This has been Mr. Holsey for H Squared Sufficiently Understood Science.